when we go down into turn one.
Green flag.
A big mess down here in turn one.
Newman gets a big jump.
Yeah, but that's going to open the door for Larson with those 2 fresh tires. Oh no, that's 17 got in the side of 42.
They're okay. They come off the corner hard.
Here comes that 18 down on the inside.
McMurray slowing to the back.
Watch that 18 go into turn 3.
Inside Stenhouse.
Well,
way inside.
It's stuck.
Yeah, but so did the 42 of Kyle Larson, who's going to get a big run here off of turn 4.
And we're coming to the white flag. 1 to go.
Keselowski inside Harvick. Working on Stenhouse.
Oh, Larson got a little bit loose, but still gaining from the 31 at Newman.
Newman has set sail, boys. I tell you, he's got a nice lead. They're not going to catch him.
3 wide mid-pack, but out front, Ryan Newman, Kyle Larson to be second again.
So close, but I don't think it's going to be enough.
Off turn 4. Hello, Newman. Ryan Newman wins for Richard Childress Racing. Larson, Kyle Busch, a photo finish for Keselowski and Stenhouse. Give 4th to Stenhouse, 5th to Keselowski, 6th to Harvick. Suarez, Eric Jones.
Well, hello everyone. Welcome. My name is Bill Magro. I'm with Intel. I'm the Chief Technologist for High Performance Computing. And today I have with me Matt McKee from Rescale, who's the Director for North America, and also Seth Morris from Richard Childress Racing, which you were just looking at, focusing on aerodynamics and improving the competitiveness of Richard Childress Racing, RCR, through high-performance computing. So you may wonder, why are we looking at a NASCAR video, and what does NASCAR have to do with this session? But today what we're going to do is we're going to talk a little in 3 segments. From Intel, I'm going to talk about what HPC is, HPC in the cloud. What does it mean? Why would you choose it? How is Intel powering HPC in the cloud, and the latest instances from AWS based on our latest processors. Then I'll hand it over to Matt, who's going to talk from Rescale and talk about how they're exposing and delivering high-performance computing through the Amazon cloud. And then finally, Seth will step up and talk about how RCR, Richard Childress Racing, is actually using it to improve their competitiveness and win with HPC in the cloud. Intel always has some standard legal disclaimers, so take a quick read and we'll move on. So the first segment here is, Intel, we power HPC in the cloud for sure, but what is HPC in the cloud, and why would you even consider doing HPC in the cloud? And that's what I'm going to focus on. So to answer that question, you have to start by asking the question, what is HPC? So HPC is high performance computing, and Intel actually thinks of it in terms of the workload as opposed to the infrastructure. And that's going to be very important later as we think about HPC in the cloud. So when people ask me, what do you do? And I try to explain to family, I say I work on HPC for Intel. They say, well, what is HPC? And you try to start to describe it. They don't want to hear about the math. They don't want to hear about the infrastructure. What always resonates people with is the applications and the impact. So high-performance computing is used, in life sciences to drive the discovery of new drugs, to improve patient treatments. It's driving the revolution in, patient-specific or personalized medicine, if you've heard that term. All of Wall Street, program trading, all the analysis, the risk, that's done with high-performance computing. These days, the energy segment, finding oil, finding natural gas, maximizing the output, so reservoir management. All of that is driven by high-performance computing. And it goes on, predicting the weather. Thousands of lives saved by understanding tsunamis and hurricanes, the paths they're taking, the surprising things they can do, like Hurricane Sandy, where it went up the coast and it took that abrupt left turn, or the recent hurricane that hit coming from the Gulf, knowing that it's going to stall and take a right turn and linger over an area like Houston, allows evacuations, saves lives. And of course, safer products. Being able to build cars that they can fully simulate them and know that in offset crashes, all these standard crash scenarios, that the car is actually going to protect the occupants and do that completely in the computer. That lowers the cost dramatically of delivering safer cars and accelerates the safer cars, because it removes the whole trial and error aspect of building physical prototypes. And the same approach is used in all the manufacturing industries, whether it's the drop testing of your cell phone, optimizing antennas for cell phones, designing more aerodynamic wings for airplanes. So high-performance computing spans all these areas, and it's also what's powering the revolution in machine learning and AI. So high-performance computing is a broad set of workloads. But at Intel, what distinguishes a high-performance computing workload from another workload? And we have 3 criteria. One criterion is that the product of the computation is based on the intent, and the intent is an intellectual product. You gain an insight, right? So whether it's in high-performance data analytics where you're studying a bunch of data and you really can't make sense of it, but out of that you get this insight. You go, oh, I see. There's a pattern there and I can act on that. It gives you advantage. If you're a scientist, it's the intellectual product of discovering and driving the science forward, or discovering a new drug candidate. It could be an intellectual product like RCR Racing, is understanding that maybe some non-intuitive design in a baffle or a shape of a car is actually going to improve their performance in a very complicated situation like drafting behind another vehicle. And I think Seth's going to show you that later. So that's the first characteristic. The second one, of course, is it has to be computationally demanding. It can't be high-performance computing if it doesn't use a large amount of compute. So we're going to focus on that. And then the third characteristic is that as you apply more resources, you aggregate resources, and you do it appropriately, you get a more valuable result. So if it's an insight, do you get a more accurate forecast of what the weather's going to do? Do you get a safer car in that cycle? Because every year there's a cutoff for changes to the design of the car because the new model has to come out. So when you apply more resources, you actually get a more valuable result. And that's very important because we think about scaling up problems, and that affects many types of workloads in HPC, but some of them are really about solving a huge problem faster, and others are about exploring a design space faster. And that's going to help us understand which HPC workloads fit in the cloud versus don't. So why are customers looking to do HPC in the cloud? There's a lot of reasons, and a few of them bubble up to the top in our market research. But there's really 2 classes of customers I'd like to talk about. One is people who are existing HPC users. Think of your Fortune 500 companies, your large industrials, all of your Wall Street banks, all of the big pharma. They're all national labs. They're all existing users of high-performance computing. Why would they want to do it? Well, imagine you're a company that's designing an airplane or some very complicated system, and you've got engineers and suppliers around the world. Being able to do your collaboration online and have access to the data where everybody can come together, as opposed to shipping data files back and forth, can actually be a big win. That's the R&D collaboration. Another one is surges in demand. Almost all these customers have their own on-premise high-performance computing systems. And in general, HPC systems, unlike a lot of IT servers, for non-HPC uses, actually run at pretty close to 100% utilization. It's a fixed resource, and you manage it with a queue. And there's always a backlog of jobs. Well, there's an opportunity cost there. If the queue gets too long, an engineer or a scientist won't submit another job to the queue because they don't want to wait. So they think very hard about what work they want to get done and how long they're willing to get it done. And so even though the utilization of the system is quite flat, there really is a demand curve that rises above. And a lot of companies are finding that if they can augment their on-premise resources with access to elastic compute through AWS and companies like Rescale, they can actually make their engineers and scientists more productive. So that's this managing demand surges. It also fits for things where there's a lot of seasonality to the usage, and I think Seth will talk about that. There's a whole racing season, and there's a time when you're intensely designing, and then there's a period where you're not doing things as intensely. So being able to essentially pay as you go and have your usage rise and fall, that's a very good fit for the cloud. There are other reasons as well that are appealing, but I want to talk about a totally different class of customer. Think about somebody who's in the supply chain to one of these big manufacturers. If I'm a very large auto company, I'm getting parts from everywhere, and I need to do a full car crash simulation to get that 4-star safety rating, which is really going to make a difference in how appealing, say, this minivan that I'm designing is going to be to families. Well, I'm getting parts from many, many different people. So I either have to take the parts, go into a physical lab, characterize them, put them under stress and strain tests, build a model, and integrate it into my car. Or I can say to the small and medium manufacturers that are supplying me in my supply chain, I need you to adopt high-performance computing. And I want you not to just give me a part, I want you to feed in a model that I can integrate into my larger model so I can do whole car crash simulation and testing. Well, that's a challenge for these small companies. Oftentimes, the small, medium manufacturers, under 500 employees, they know that high-performance computing can help them, but they really don't have access. And some of the barriers are, access to the applications because an application seat can cost tens of thousands of dollars for a single engineer. And if you don't even know what the return on investment is going to be, it's very, very expensive. It's like buying a car speculatively when you don't know how to drive, because you have to take one trip. So what would you do instead? You'd rent a car, and you'd prove, you'd say, that was pretty cool. And then you rent a car more often, more often. Pretty soon you realize that it's more expensive to rent, and then you start to balance what you own versus when you rent. And there's an analog here, an analogy with the cloud, where people, to get into high-performance computing for the first time, cloud provides that vehicle. And then as their usage rises, they may balance how much they buy and use HPC through the cloud versus things that they put on premise. And many people who are brand new to the cloud decide never to even put on-premise infrastructure. It might make sense for their level of usage to just access HPC through the cloud. So I think everybody knows that behind cloud computing, Intel is providing CPUs. But I want to talk a little bit about the performance, security, and agility and how these come together. You can't do high-performance computing without performance, so Intel is on a relentless drive for performance. But the cloud is about taking a pool of resources and making it feel like it's your own. So it's about safely carving things up, making you feel like you own your own resources, even though it's a part of a larger pool. And security, obviously, is a very large part of that. So we have a lot of features inside of our processors and platforms that companies like Amazon build on top of to provide you that isolation, that security, and do it in a way that you don't have to give up significant performance. We also have virtualization features, again, that work in conjunction with the security features to ensure that that performance continues to come through, despite the fact that we have all this agility and the ability to carve things up and make it feel like it's your own. So Intel recently announced something called the Intel Scalable Processor Family, based on codename Skylake. And that processor generation is now available through Amazon Web Services, known as a C5 instance. And this is a compute instance that's really very, very suitable for high-performance computing. So if we think about the spectrum of workloads that I was talking about before, some of them, like weather forecasting and climate modeling, really do need dedicated supercomputers. But there are other things like design space exploration, or integrating the small variations in a model, or testing small variations in a model or a design for later integration into a large model. Some of those can actually run on smaller number of instances. So when the instances become more powerful, like the C5 instance, it means that you can do more of your HPC in the cloud. So the boundary between what needs to run on-premise in a tailored system versus can and probably should run in the cloud is moving with every generation. The C5 instance allows for up to 72 virtual CPUs. It's based on our Skylake processor architecture, which has a lot of innovations and enhancements in it that were driven specifically for high-performance computing. One that's notable is AVX 512, and I'll show you on the next slide what the performance impact is of that. But it's wider vectors and allows you to do up to 32 double precision floating point operations per clock, per core. It's a tremendous compute capability, an increase of 2x over the last generation. To keep the compute balance, we've added memory channels and we've increased the speed of the memory channels. So 50% more memory channels, each running at a higher speed. Peak bandwidth can be as high as 66% higher than the previous generation. And you can see that Amazon has also increased the amount of networking bandwidth to these instances and the available memory. Again, the whole goal is about keeping a balanced platform. So the C5 is a great instance type to use for traditional simulation and modeling, but also high-performance data analytics and machine learning. So with these recent advances in the processor, why does this matter? Well, again, in high-performance computing, applying more resources appropriately gives you more value. That value can come through faster time to completion in an existing model. That would be important for being able to get a 12-hour weather forecast in an hour instead of in 3 hours, for example. Getting that information sooner is more valuable. Could also be greater accuracy. We talked about finer meshes, and I think you'll hear from Seth later about how RCR is using the treadmill of performance that comes in high-performance computing to actually get more and more accurate models by driving to finer and finer meshes, and allows them to see features in the aerodynamics of the car and the flow patterns that actually give them a competitive advantage. And of course, you can also maybe work with a more sophisticated algorithm that gives you higher confidence. So you get an insight. There's always a question of how much can I trust this result? So more performance manifests itself in terms of value in a number of different ways. But in high-performance computing, it's all about getting those greater insights and more value by applying more resources. So as we tested the new Intel Skylake or Intel Xeon scalable processor family and compared it to the previous generation that powers the C4 instance type, I told you about the 2x in peak performance available through the AVX 512. When the applications are appropriately enabled, we went and looked at both performance on traditional infrastructure and also directly comparing C5 to C4 instances in the Amazon cloud, and on HPC applications including weather forecasting, climate modeling, computational chemistry, quantum chromodynamics. There's a broad range of applications. We see gains on the order of, you can see 1.74x up to approaching 5x gains. And this is coming through those vector enhancements, the memory bandwidth enhancements. There's microarchitectural improvements we've made. We've replaced the ring that happens inside the interconnect with a mesh. We've changed the cache architecture. So there's almost a complete overhaul of the Xeon processor under the covers while maintaining compatibility that's driving these performance gains. So how do you select which HPC workloads can run in the cloud? I touched on this before, but I want to return to it. There really have been two considerations traditionally. One of them is just comfort. It's around the intellectual property and security and your comfort of putting something in the cloud. HPC is all about an intellectual product, and that means the data, the models, your algorithms, all of those things are your secret sauce. So if you're a chip designer like Intel, or you're a car designer, how comfortable are you putting that data in the cloud? Well, that's an answer that really isn't about technology. It's about culture. It's about observing and seeing where data breaches occur and don't. One thing I can tell you is that the comfort level of putting sensitive data into the public cloud, that people are getting more and more comfortable with that. In fact, many companies are now finding and starting to understand that a company like Amazon, who's aggregating so many resources, can actually go after top security talent in a way that maybe they can't on their own. So some companies are actually finding that they're more comfortable with their data in the cloud than having it on their own premises. So that's one big factor. Another big factor is just the technical characteristics of the workload. I show here two extremes. One is what we call cluster HPC. These are the tightly coupled workloads I was talking about before. For example, Seth is going to talk to you about aerodynamics calculations. How far you push those in the cloud will affect how well the cloud scales. Those are single problems that are getting divided up into lots of small problems, and those small problems are computed locally, but then they pass messages back and forth. And so things like consistent performance across the nodes, dedicated access to instance types, highly reliable and predictable messaging performance, all are big factors in being able to do that. And that's currently a limiter of which workloads can go in the cloud. But there are features that are in AWS, and more are coming all the time, that increases the scope of workloads that can run in the cloud. So certainly using the large compute instances is a good plan. Go with those C5 instances so that you get the most you can without having to go to the network. The enhanced networking, we talked about enhanced access to storage in the C5 instances. Networking performance is improving with every generation. And also policy like placement groups, where you're actually telling AWS, hey, I'm doing high-performance computing here. I'm doing something tightly coupled. Amazon will actually put your instances close to each other so that they're not messaging from opposite ends of a data center. Those are called placement groups. At the other extreme is what we traditionally call grid computing or high-throughput computing. This is still part of the overall high-performance computing umbrella in the sense that it meets those three criteria I talked about before. But in this case, these are loosely coupled. Sometimes we call it embarrassingly parallel. Sometimes we call it pleasingly parallel calculations. This might be something like a design space exploration. I've got 7 different types of foam that I could use for a steering column, or on a steering wheel, or in a dashboard. I'm going to do repeated crash test simulations of just that one subset of the car, and I want to know which one is provides the lowest injury rates across a number of different models. Or maybe I'm screening a genetics database with a bunch of drug candidates, for example, doing a life sciences. These are the types of problems that you're flooding the system with lots of different parameters, and you're doing the same thing, and there isn't a lot of communication. You see this coming up in life sciences, pharma, financial services are the primary places using this. And here you don't really need tightly coupled. You just need a nice queuing system that can manage all your workloads for you. And I think Matt is going to talk about Rescale's platform and how it gives you access to a wide range of instance types to cover the spectrum we're talking about. So I talked earlier about the barriers to HPC in the cloud. One of the biggest ones is, not just the access to the applications, but how do you even build up the right kind of platform in the cloud? If you assume that somebody is not an HPC user today, one of these small, medium enterprises I talked about before, if they have an IT administrator at all, chances are that someone is a specialist in Microsoft Windows running local applications, or maybe they're even a specialist in web apps because this company has decided to do everything through the cloud. The chance that they actually know how to build a Linux cluster, set it up with the right shared permissions, global file systems, high-performance messaging, the chances of that occurring is really, really low. So if you want these applications that need the tight coupling and run message passing to run in the cloud, and you don't want to rewrite the applications, and nobody wants to rewrite their applications, it's critically important that you have a consistent platform, meaning what do the applications see as they look down from the traditional HPC cluster into the cloud. And this is something that Rescale automates for you so that you don't have to think about it. You say, I want to run this application, you submit your workload, and it takes care of creating that consistent and familiar HPC platform in the cloud. The next thing that Rescale does, it's just one of the reasons we're excited to work with Rescale, is they actually provide pay-as-you-go access to all of the key applications. I think Matt's going to show you that. So that's the other critical barrier, is getting access to these applications, because without the applications, you can't do your work. And so with that, I'd like to hand it over to Matt.
Thanks, Bill. So I was at Supercomputing 2017 a few weeks ago, right before Thanksgiving. And for those that are unfamiliar, SC is the largest high-performance computing conference in the world. About 14,000 people come and to learn about next-generation technology. And here we are, less than 2 weeks later, and we're learning about the same next-generation technology that we heard from Intel at Supercomputing, and now we're at AWS reInvent and hearing about that same next-generation technology being rolled out in massive capacity on Amazon Web Services. And what this indicates to me is that we're at an inflection point. This would not have happened just a couple of years ago. So I'm with Rescale, as Bill introduced, and the reason why we get the honor of sharing the stage with Intel, who creates some of the greatest architecture in the world, and then also Richard Childress Racing, responsible for 17 championships in NASCAR, is that we provide the technology to help you deploy and exploit with this world-class capability into the hands of the engineers, researchers, and scientists. So the great thing about being here at reInvent, I'm sorry about that, is that everyone here kind of gets the cloud and its benefits. And Bill reviewed some of those, such as collaboration, demand surges, reducing your CapEx, and then access to scale. However, before I talk about the how, I will add a few more whys that I've seen from our customers using the cloud. And the reason why I really like this quote, and Tim is kind of like a CIO advisor that you'll find is fairly prolific on social media, is because I think that everyone kind of gets the why for the most part. There are some specifics that I want to add that are unique to HPC, but really I think we're all thinking about what's the how? What's the best way to do it? How do I do this in an easy, repeatable manner? And how do I make it accessible to the non-experts? A lot of us here would consider ourselves experts in AWS and AWS services, but a lot of the end users are not. So I'll first, and I'll get back to this picture in a second, but The first why, as I'd say, the cloud enables new approaches to problems. So take for an example, one of our automotive suppliers, and Bill, and we did not coordinate this, but Bill was talking about those suppliers that exist under those major OEMs in the automotive space. And this particular automotive supplier was looking at a particular design study and a technique that was going to save them about $2 to $5 million in their overall engineering costs of a specific component. However, on their current infrastructure, it was going to take about 80 days to complete that design study. They needed it done in about 2 weeks. On the cloud, they could get it done in 1 day at a lower cost. So without the cloud, they would not have been able to pursue this particular design study. Now I'm going to get to the picture, which is Boom Technologies. So those are not familiar, Boom Technologies, and this is their XP1 demonstrator, is developing a commercial supersonic jet that would get 40 passengers from LA to Tokyo in about 5 hours. That trip is about 12 hours right now. So this is taking everything that we learned from the Concorde, and it's in the things that didn't work out too well for the Concorde, and bringing that with all the modern techniques. Well, how is Boom doing all their design and engineering studies? The first thing they did as a startup is they did not go out to and buy a massive on-premise HPC system. Not only could they not afford it, but it also did not fit the way that they were doing their work. And what is that way? Is that they are not using traditional CFD methods. And the method they're using allows them to do their CFD design studies 20 times faster than the traditional methods due to the elasticity of the cloud. The second why that I want to talk about is enabling your teams to fail fast. And I know that doesn't always sound, that can be a little bit counterintuitive, but when you create a situation, when you have queues and you have constrained resources, what you can't do is understand which paths are unproductive sooner. And when you create an unconstrained environment, you can get to the no's, and there's a lot more no's in the design cycle than there are yeses, to get to that final design a lot more quickly. And the third why is you can enable organization to react to new requirements. We were talking to one of our customers who's a Fortune 10 company, and you would think that an organization like this that thrives on innovation would be able to react to a new requirement quickly. But actually, it takes them 12 to 18 months to react architecturally to a new requirement coming up for their organization. That's simply not acceptable in this day and age with the pace of innovation. And with the cloud, they can react to that requirement in a matter of hours. And then lastly, you can provide a higher service level at a lower cost. And cost is a big concern in the HPC community about, especially with those that come from on-premise architecture. But with the cloud, you can provide a higher service level at a lower cost. Now, there's a lot to expand on that. In fact, I did an entire webinar on it to talk about why that's the case. But unconstrained resources do not mean unconstrained costs. And one of the ways that you do that is through something like Rescale. So again, those are the whys, but what's the how? With constant innovation in the architecture that we just heard from Bill, constant innovation in the applications and new methods, how can you stay just as agile in your deployment of AWS as AWS is staying in their deployment of new architecture? So I'll talk about some of the challenges there. First, the challenge is the installation, availability, and maintenance of hundreds of applications and thousands of versions. So when we talk about some of the skills that an HPC administrator might have, it may be a lot around just doing a lot of application maintenance and installation. It's not very sexy work, but it's absolutely essential to get that tuning that you need to be able to do this type of HPC, these HPC workloads. So these codes can be either open source, they can be commercial, or they can be proprietary codes. Furthermore, with the elasticity of the cloud, many software vendors are developing elastic models for licensing, allowing software to scale alongside the hardware. So how do you actually have a single environment where you can have your users take advantage of these elastic software resources alongside hardware? And how do you support a variety of different licensing models? So we talked about on-demand, but you also have a lot of licensing models that are on-premise. So that's one of the challenges. The second challenge is tuning those thousands of application variations on a variety of architecture. So different problems demand different architecture. And anyone that has discovered had a job fail due to running out of memory, in a constrained environment with on-premise resources, you're typically always making compromises on the type of architecture you're using. You're trying to go down a generalized path as much as possible as can make everybody happy. But the cloud does not require you to make those type of compromises. And instead, you can align your work with exactly the instance that you need. And in this case, it just takes an example of a variety of different AWS architectures that are better for different types of problems out there. And the fracturing and the divergence of software needs continues, especially as we see the rise of machine learning and deep learning. So you can always choose the right architecture for the right model, and there's really no need to compromise. And really the third challenge that Bill also hit on was building a secure layer for this that manages the movement of important data to and from some of the most secure data centers in the world in Amazon Web Services. So this includes segmented user access, data encryption, ITAR controls, and any other security protocols that your organization has. So we know, Bill talked about, AWS, but there's also an entire shared security model that there's a number of responsibilities that fall on that customer organization from being able to deploy HPC effectively. The next challenge is provisioning and deploying this all to a diverse set of users and administrators in a simplistic user interface. So how do you ensure that users are spending all their time on critical design challenges and no time spending fumbling around using a hard-to-use system? And then last, how do you do this around the world in a seamless manner to support geographically diverse organizations? So Rescale answers these challenges, automating all the services and tools required in deploying AWS for high-performance computing. In a single platform, Rescale creates an environment that brings together your applications, compute capabilities, systems administration, and security capabilities that organizations need in a very, very simple-to-use platform. Moreover, AWS, as you see here, Rescale does this in all the AWS data centers around the world for those geographically diverse organizations. So from here, I'm going to kind of let the platform speak for itself and show. Let's see here. Get this started.
In this video, we will show you how to run an ANSYS Fluent simulation on Rescale's ScaleX platform. Once you log onto the ScaleX platform, click on New Job to start a new simulation and give the job a unique name. In this video, we will set up a car external aerodynamics CFD simulation using ANSYS Fluent. Step 1. Upload input files from your local computer to Rescale. We uploaded a Fluent journal file and used an archive case as the inputs. Next, choose your software. In the software section, you will find a suite of ANSYS engineering simulation tools. Here we choose ANSYS Fluent for this demo. In the command setting, enter the file name for the Fluent journal file. Then, choose the license type. On the ScaleX platform, you can access ANSYS Elastic Licensing, tailored for cloud computing, which provides flexible access and time-based usage. Or you can use existing license by entering your ANSYS license file, ANSYS server, and project code provided by Rescale. Clicking Next will bring you to the hardware setting page. Instant option allows your jobs to run immediately upon submission. On demand lowers the compute cost, while your job may be terminated and restarted, at most one time. Besides the primary core types shown here, you also have access to traditional specialized core types. As you increase the number of cores to 36, you will see the hardware summary increase on the right side. The next step in the job setup is to enter optional post-processing scripts. However, we will not need it for this particular demo. Finally, review your setup. Once you confirm the software and hardware settings, your job is ready. Once the job is submitted, you can monitor the progress on the status page. Rescale will take a few minutes to verify the inputs, boot up, and provision your cluster. Once the job begins to run, you can track the status in real time using live tailing. You can view the output files as they are being generated directly in your browser, such as the log files and convergence plots, to verify the simulation is converging as expected. Once the simulation is completed, you can verify that no error messages were created. The output files will automatically be uploaded to cloud storage, and the cluster is automatically terminated. You can view the output files and download the results back to your local computer. You can also launch a Rescale desktop to post-process your simulation results. By clicking the Visualize button, it will load a pre-configured Rescale desktop session with ANSYS Fluids Desktop and attach the output files from this job. The desktop session will take a few minutes to start the server. Once you see the server started status in the log, you can click Connect to launch the remote desktop session. By connecting with in-browser desktop function, you can access Rescale Desktop within your browser window. You can launch a Fluent GUI in Rescale Desktop and load up the results for post-processing. The job result files can be found in the Desktop Attached Job folder. Then, we can generate a few contour plots to visualize wall shear stress, static pressure distributions, and more on this car aerodynamic simulation. And that is how you set up and run an ANSYS Fluent simulation on Rescale. Thank you.
Okay, so I believe the platform speaks for itself, so in terms of ease of use. But in this shared responsibility model, what Rescale replaces is any systems integration, security architecture, and custom software development to give an organization the agility to always stay on the latest Intel architecture. So HPC on Rescale allows you to deploy instant access to unlimited architecture, a diverse set of architecture so you can match the software to the right compute type. It gives you tuned applications to basically deploy that HPC administrative capability in an automated fashion to your organization. And furthermore, you can avoid the queuing and constraints of an on-premise system. Rescale is the easy way to do the how, and so you can actually realize the benefits of the why. So this is quicker innovation cycles, faster time to market, and in the case of NASCAR, you can be the fastest car on the track. So with that, I'm going to turn it over to Seth.
Thank you. All right. I'm Seth Morris, CFD team leader and aerodynamicist for Richard Childress Racing. So just to give you a background on the history of Richard Childress Racing. Richard started racing when he was in his 20s. He bought a $20 taxi cab. He was the engine builder, the mechanic, the race car driver. He basically did everything and then built it into an empire. Eventually teamed up with Dale Earnhardt Sr. and won 6 championships at the top level. And then currently we have hundreds of race cars that we build every year. We're an engineering-driven company with 15 championships and over 200 NASCAR victories. We're the first organization to win titles in the top 3 National Touring Series. Richard was recently inducted into the NASCAR Hall of Fame this year. So we have to build basically these cars from the ground up per the NASCAR rules. Engine blocks and heads are supplied by General Motors, but we machine them to our spec. We design and fabricate all the chassis components, machine suspension components and whatnot. And then of course, the body panels are supplied by General Motors, but we shape them to our aerodynamic specification. The aerodynamic specification is driven in large part by the CFD. So here's a quick flow chart of the aerodynamic development process. You have an idea that drives into the CAD model. We may do a CFD subsystem, which then drives back into an idea or goes to the full car CFD. This sort of validates or weeds out any bad ideas, runs the wind tunnel back to the race car, and then that generates our idea loop or our development loop. Here is a picture of a mesh. So we generate very large meshes, and they're ever growing, and that is part of the reason why we rely on the cloud, because our designs and our understanding of the car have to increase as time goes on. So this is an example of the flow field underneath the car. This is a very specific attitude of the car. If the car goes into the corner, it may have a different flow feature under here. And as we want to be able to understand all these differences, we may want to have a mesh that is more universal to different attitudes of the vehicle. If we do that, then you increase the size of the mesh, and of course we need to have bigger resources to be able to make these calculations. So typically we're running about 16 hours for a 200 million element mesh on 512 cores. Fluent linearly scales in the range that we're operating in, which is kind of the bottom of this bottom right plot. And then of course, throughput also is dictated by read and write time. Fluent has increased their ability to read and write data, their latest releases. This is an example of a drafting case. So we don't always run drafting cases depending on which race that we're going to be attending the next weekend. We may be looking at drafting versus, which is a drag limited track versus a downforce or a grip limited track. These cases take more time to solve, and of course, using the cloud and having the ability to surge on our processing is important to be able to put these through because they're very computationally expensive. So we use Fluent as our CFD solver, and we don't just look at aerodynamics, but anything that fluids interact with. So that could be engine cooling, fuel flow, heat exchangers, internal and external aerodynamics. And the reason we use Rescales, because we have no existing infrastructure for HPC. All of our IT is usually dedicated to data management at the track and issuing computers and things like that. And then of course, scalability is the biggest thing. Here's an example of our throughput by month. So we have a very non-constant throughput, and this is something that was spoken about earlier, that if we were limited to an on-premise HPC cluster, we would attempt to just maximize 100% utilization all the time. But since we are not limited to that, we're able to take on different tasks and of course adapt to some of the issues that happen with employing people. If you have 2 people, maybe they're 2 new people, you may have low productivity as they start, but they ramp up, and then maybe you have problems with the solver or some of the solutions, and this demand kind of goes down because we're working through some of the problems, and we're able to adapt to any of the problems that we're having. And that's it.
Yeah, so I'd like to invite Matt back on stage. We'd be happy to take any questions from the audience, if there are any. If you have a question, if you don't mind stepping up to the mic in the aisle, that way everybody can hear you, right next to you. Okay.
Does Rescale provide, we're using CD adapter. Do you already have an analysis of what's the best instance type for all the software that you support, and already have that matrix built together?
Yes. So we do quite a bit of benchmarking, and we have an entire team that sits around and tries to understand what's optimal. Because it's not always based on just the application itself. It could be the type of model you're running, right? There's lots of, as you know, Seth mentioned, there's lots of different CFD models out there for, you could be looking at a combustion scenario versus an aerodynamic scenario, and there's going to be different needs there. So what we do is we have a lot of pre-baked information that we have gathered from our 6 years of doing this on different AWS instance types. But we also work with your team. We do a series of benchmarkings ourselves with you. To be able to lay that out for your engineering team. So we're kind of, in addition to actually providing the software that does all this orchestration, we have a very robust support team that is basically your HPC cloud experts on demand.
Are there any other questions for us? No? If not, then thank you very much for coming to this session. Have a great day.